Okay, thank you very much. Also, thank you very much for this invitation. Yes, it's a very nice place to be here, and also thanks to the organizers for organizing this. I will be talking about clustering of trajectories, and so I hope I speak loud enough. I cannot speak so loud, so if you don't hear me in the back, then it's okay. Good. Right. So what do I mean by trajectory? So I work in like these two research projects. So I just put up some pictures here, just some impression of what could be meant by this. So trajectories just give us a way to represent observed motion, and they could be so in some system, like in a Lagrangian way. Following along, giving us the motions of the particles in some system, or it could also be tracking the movements of a person, and or migrating animals. But so they don't have to be in 2D. They can also be high-dimensional trajectories, tracking the joints of the motion of someone. But I will talk about this later a bit more. This is just to get started on the motivation. So if we want to cluster trajectories, we have to have a notion of similarity or distance. And I think the most straightforward way to define this similarity is the Fréchet distance. And how do we represent these trajectories? So they are just observation sequences of observations of some moving person or particle. And so for us, they're just polygonal curves. So we just linearly interpolate between two observations. And then we can also reinterpret this thing as a parameterized curve, so just a mapping from the 0-1 interval to RD, the ambient space of the trajectory. And now we can look at these trajectories and we can reparameterize and just basically focus on the trace of the curve, the order in which this trace is followed along by the trajectory, and then minimize over all possible reparameterizations and try to find the best fit between two trajectories. And that's how we measure the distance. So we take this maximum along the two curves of the distance, so kind of like an L-infinity distance, but then we minimize over all possible reparameterizations. So I think this is the kind of the most natural way to define the distance or similarity of two trajectories or two parameterized curves. And now, since we're optimizing here over an infinite set of reparameterizations, you may wonder, can we actually compute this? But there's actually a relatively easy way to compute this via dynamic programming or continuous dynamic programming, looking at the free space diagram, which is, so you look at the joint parametric space, and then a point represents, so a point in this joint parametric space gives us two points, one on each curve. And then it's in the so-called free space if the distance is smaller or equal than delta. So here what we mean by this is just Euclidean distance. And now what you're looking for is a monotone path through this free space. And if and only if the Fréchet distance is smaller than delta, then there exists a path that, a continuous path that is monotone in both coordinates that goes through this space. And so if I go back, so if this delta is a bit too small, then here there is a path, but there's no monotone path. If we make delta a little bit bigger, then there is a path. And so we can test whether the distance is smaller or equal to delta by going through this free space diagram. So this is all well known, but what we want to do is we want to solve clustering problems under this distance measure, okay? And we care about these curves being kind of this Fréchet distance defining similarity in a continuous way. But just in case maybe you've already seen work on the Fréchet distance. So another common way of defining the Fréchet distance is in the discrete setting, where we only measure the distances between the actual points. So we don't take into account this linear interpolation between two neighboring or consecutive points. And then this free space diagram just becomes a matrix, and we want to find a path that only like a path through these entries of the matrix. So I don't really want to go further into this. I just want to say there is a difference between the two. So the discrete Fréchet distance actually converges to the continuous Fréchet distance if you sample the curve densely enough. but otherwise they can be quite different, right? So the edge links here could incur an error kind of that is additive. So if you don't have a densely sampled curve, then they're not very similar, not necessarily. And we want to focus on the continuous Fauché distance. And when I talk about clustering, then so the first, like mathematically, the easiest way, or the first thing that comes to mind is maybe the minimum enclosing ball in the metric space, right? Which is like a clustering just with one cluster. You want to find the element of the metric space that minimizes the maximum distance to your input points in this metric space. And then if you want to find a clustering, then maybe you have a parameter k. You want to find a partition into k groups so that these groups can be covered by balls of small radii, and that's the k-center problem. So k-center problem has this fixed parameter k, and you want to minimize the maximum radius of these minimum enclosing balls that you find. Okay. So we could apply this to our problem because the Fauché distance is a metric. I mean, and you also can use this in non-metric spaces, but so it's a distance measure. But we want to modify it a little bit because if we would just apply it directly, then we might get an overfitting problem. So if you take two curves, A and B here, then you can see that the center, so the curve that minimizes the maximum distance, picks up on all of these small dents here. So you can also increase this, and you get a center curve that you may get a center curve that has the same complexity as the input data. So, and that's not really what we want from a clustering. We want the clustering, the cluster centers to kind of represent the set and give us some kind of summary. So that's why we look at this KL center problem, where we require the cluster centers also to have small complexity. So there should be only few vertices on the center curves. So just like we say, the clustering should have only k clusters, we now say also the cluster centers should have only L points. And so this problem is not so difficult to solve if you are if you're fine with approximation algorithms. So there's a relatively easy 3 approximation algorithm, which you just pick any curve and then compute a piecewise linear approximation, what we call a simplification of that curve. And then in each step, you take the curve that has the largest distance to your set of centers. You pick that one and compute the simplification. And this way you define centers in k steps, and that will give you a 3 approximation. So this is an adaptation of an algorithm called Gonzalez algorithm. In metric spaces, normally it gives you a 2 approximation. Here we have this additional step that we require these centers to be small complexity. So we also approximate the centers. This here, the simplification, this is basically this is the curve that best approximates the curve Q under Fauché distance, but it only has L vertices. Okay, so for one center, just with one input curve, this would be the optimal solution. Yeah, so using triangle inequality, you can show that this gives you a 3 approximation. But yeah, so maybe you think 3 approximation, maybe that's not so good, but we can also show that this is NP hard actually to show something much better, so it's hard to approximate. We have different approximation factors here, but we think that probably this should probably be a 3 minus epsilon. So getting anything better than factor 3 in the setting that we just saw, it's probably an NP hard problem. And if you want to go to approximation factors that are much smaller with parameterized with this epsilon, then you can do that if you allow to be exponential in the number of clusters and the complexity of the cluster centers. So that's also possible, at least in 1D, if the curves are just the ambient space is just one-dimensional. So I didn't really tell you anything about these results because this is actually just a prelude to the problem that I really want to talk about, and this is the subtrajectory clustering problem. Because if you just have curves and you put them in a metric space, that's not very realistic. So there's only few application scenarios where your curves are already so well defined and they start in this point, they end in this point, and you want to cluster them kind of as whole curves. So normally what you do is you have some, maybe some GPS tracker, you put them in some, if you're lucky if you catch the animal, and then you put the GPS tracker and then it just sends the data until the battery dies. So you get these really long trajectories and you don't really know where your patterns that you look for, where they start and where they end. So the problem is actually different. So it's a clustering problem where the elements that you want to cluster are just kind of, so any interval of your trajectory would qualify as an element of your clustering, right? And how do you define this as a clustering problem? Because any curve has, I mean, there are many sub-trajectories or many sub-intervals or sub-curves that you could look at. Not all of them are relevant. How do you define a good optimization problem on this that optimizes both like the splitting of the trajectory or segmentation and the clustering at the same time? So again, this is here, there's some pictures. So here at the top left, you can see my mouse pointer, I hope. This is kind of the easy case. This is some data set with homing pigeons that are released at some point and then they all fly to the same point. So this is the easy case. What we're now interested in is something else where you just have these particles that go, like here, these ocean drifters, and what you're interested in are these sub-trajectories that form clusters. So for something like this, we want to compute maybe, or when you have this full body motion, you want to have maybe a segmentation into clusters, like repeating movements that the person does. So that would be something that you're interested in. There are many other application scenarios. I will talk later at the very end, if I have time, about these two and show you some results of our experiments, but there are also other trajectories you can think of where you get these long trajectories. Okay, so how do we define this optimization problem? So let's go back to principles, first principles, and let's look at the set cover problem. So set cover problem is one of the famous NP-hard problems that is kind of underlying many of the optimization problems we want to solve, discrete optimization. You probably know the definition, but just to make sure that like we all remember what it is. One way to define it is you have given a bipartite graph, and on one side here, these are the elements of your ground set, and the other side, these vertices and connected edges, they define subsets of the ground set. So any vertex here, vi, v1 for example, defines a subset. If you look at the neighborhood of the vertices that it connects to in the ground set, that's the subset that is represented by v1. Okay? And in set cover, what we're interested in is we want to find a subset of these minimum size subset of v, such that with their neighborhoods they cover all of the ground set. Yeah? There's another problem that is dual to this actually. It's called the hitting set problem. There you also have given a bipartite graph, or we also say a set system. And here you want to find a minimum set of points of the ground set so that all of the sets are hit by this set. And this is the same problem if you just dualize. So if you swap the roles of u and v, and you also get a set system. It's the dual set system. And then a hitting set in that system is a set cover in the other one. Okay? And also minimum size. So it's the same problem that they optimize. You just have to dualize. If you have an algorithm for a hitting set, you can solve set cover if you apply it to the dual set system. Okay. Now comes, so what's the relation to clustering? Well, you can think of this clustering also as a covering problem. If you think of the k-center problem, so it's not exactly the same, but if you look at the decision problem, then it's the same for k-center. If you fix the radius, you want to know, can I find k-balls of radius of this fixed radius that cover my input set? And so here we have a problem because this input is not a discrete, it's not a finite bipartite graph, because any point, any center in the plane is eligible to be a center. But if you look at the dual, So you put these balls of fixed radius around your input points, then you get this arrangement and this decomposition of the plane. And for any cell in this arrangement, if you put the center there and you move it inside the cell, the coverage doesn't change. Okay, so that's exactly the definition of all the points in this cell. So now we do have a discrete set of points that are eligible as centers, because it doesn't matter which point in this cell I pick. So I get a discrete, a finite representation. So that's why this is useful to have this point of view, right? So the other take-home message is, so set cover is, it makes sense to use it for clustering problem. So now comes my most important slide of this talk. This is a definition of the subtrajectory clustering problem as a set cover problem. It's not finite, not discrete, but we can, using some tricks, we can make it discrete, at least on one side. And it goes like this. So we have to define the set system, okay? And in this set system, our ground set is the curve. We want to cover the curve. Any point on the curve we want to cover. It's an infinite set, but let's not worry about that for now. And a set is defined by another curve, a cluster center. And now I just take the union of all subtrajectories, all subcurves of P, of my input curve P, and I take all the points on those subtrajectories, and they are all covered. Okay? So it's a bit weird because, okay, I look at this metric ball. The metric ball contains a subcurve, but then I actually just break it down to all the points that are on the subcurve. Because so I'm not interested in covering all subtrajectories because lots of subtrajectories are not meaningful. I just want to cover the curve, okay, with these type of sets. Okay, so now we do, again, so we use approximation to make the problem better, easier to handle, right? Because you cannot optimize over this infinite set. We compute a simplification of our input curve, and then we only consider subcurves on this simplification as centers. And we also evaluate our set cover just on this simplification. Okay, and so I'm not going to go into much detail of why this works, but this gives a bicriterial approximation. We only lose some constant approximation factors if we do that. Actually, we also just need to look at sub-edges of the center of our curve to get a clustering, approximate clustering. And now we have actually a nice property, because now we are in this free space diagram. We take this free space diagram of this simplified curve with itself, and we're now interested in finding a set of intervals on this vertical axis, so that when we look at maximal paths in the free space diagram, when we project them, so within these intervals, when we, or from this line to this line, from start to end, when we project them down, we want to cover all of the curve with these intervals. Okay, so this is now the problem we're looking at. Again, so we don't have a discrete set yet because there's still infinitely many curves that we now can consider, right? But this free space diagram has some nice properties. So as I said, so our input are piecewise linear, so polygonal curves, and in that case, this free space has this nice property of being convex in each cell, and we can look at extremal points within each cell. And so here's an example of what this could look like, but there's a case analysis. There are a couple of other things, extremal points we have to look at. But the intuition is the following. So if you take any solution, so any covering with paths, and now you extend these paths so that you don't lose any coverage, but you get to these canonical points. And that allows us to just look at a finite number of candidates. And now we have a set system where we can optimize set cover in a discrete optimization way. And so because I don't have much more time, I cannot tell you all the details, but you can ask me later. And now what could we now use? We have the set system, and maybe you have to believe me, but given a set of candidates, we can also evaluate the coverage. So it's not so hard. So we could apply greedy set cover now, for example. But what we did is we wanted to get a better approximation factor than greedy set cover, because greedy set cover gives you only log n approximation factor. And in general, there's not much you can do, actually. You cannot get better approximation for general set systems. But if the dual set system has small VC, so-called VC dimension, then you can get better approximation factor. So that's why we're interested in the VC dimension of the set system. The VC dimension is defined as follows. So we say a subset of the ground set is shattered if, when we restrict our set system to this set, then all subsets of the sets are contained in the set system. So, and the VC dimension is the largest possible set that is shattered. So it's a measure of complexity of the set system. So if you have the power set, then this has the largest complexity because any subset has all subsets are contained in the set system. But many set systems that occur in real life don't have this complexity. They have low VC dimension. And here you could, for example, think of just a set of rectangles in the plane, and this VC dimension is 4, because so any set of 4 points, these are 5, but if you imagine 4 points, any set of 4 points can be shattered because I can represent any subset of the set as an intersection with a rectangle. But if you have 5 points, then there's always this point in the middle where you cannot exclude it from the set. So you cannot represent the set that has only those 4 points on the outside and not the point in the middle. So if I want to represent it in this form as an intersection with a rectangle. So the VC dimension is definitely smaller equal 4, and for 4 points you can always do it in a plane. And there's this important theorem by Hauser and Welser that's called the epsilon net theorem, which says, so for a set system, if it has small VC dimension, then just by taking a random sample, just uniformly drawn from the set system, from the ground set, you get with good probability an epsilon net. An epsilon net is actually a hitting set, so it's almost a hitting set. It's a hitting set for the large sets. So for the sets that cover a fraction of at least epsilon times the size of the ground set. So for small VC dimension set systems, we can get this epsilon. We can get this epsilon net, which is almost a hitting set with just by random sampling, and where the size of the sample depends on the VC dimension. And there is an algorithm by Driemel and Goodrich that uses this to get actually hitting set. So what you can do is you can take a random sample and then check if it covers your ground set. If there's a point that's not covered, then it must be a small set that in the set. So it must be a small set that is not hit, and so I just multiply the weight of all of the elements of the set with a factor of 2, and then I sample again. And every time as long as I don't have a hitting set, I do this. And by looking at how these weights develop, you can see that So the hitting set the weight of the hitting set will grow will grow much faster than the entire set system. So in the end, so after log n rounds, you actually get the hitting set. This principle is also called MWU, the multiplicative weight update method, which is also used in many other contexts. So that's what we wanted to use, and for that we had to analyze this VC dimension of the set system. Just looking at this very small example, if you think about all the possible paths that go from this cell to that cell, maybe if you squint your eyes, you can believe me that the start and end points lie in this rectangle. So the set of candidates that cover a point T in the middle here, you can actually think of this as a rectangle. So, like, we can kind of reduce it to analyzing rectangles, except we have unions of rectangles, but doesn't matter. So we can analyze the VC dimension of our set system and then get better than log n approximation factor. And what we get from this are, well, there's a couple of results. Actually, the last one is not from us. It's a newer paper by van der Horst and Oppelders. And so we can get better approximation factors, but then when we wanted to implement this, we realized, maybe we should have known, the constants are way too high, so this is not practical, these algorithms. So in the end, actually, we use greedy set cover, so we get log n approximation. And then so the running times are quite prohibitive for large data sets. So there it really matters how you define these extremal points or how big is your set system. I won't go into details. If your curves have certain properties, like being C-packed, we can get it better. And now I promised I show some experimental results. So it actually works. This set cover way of defining subtrajectory clustering. This is a data set from this CMU, Graphics Lab motion capture database, where the task is to find these sections of movement, of like jumping or walking and so on. And there's a ground truth you can compare to. So it does pretty well on terms of accuracy, but we are here, it's a bit hard to see. So these green bars, this is our algorithm, and so the other algorithms that we found that solve this set are all much slower. But this data set is not so large. There's much larger data sets that you can apply this to. And so this is a big database of ocean drifters. So these are small buoys that drift in the ocean, and they send their GPS coordinates. And oceanologists analyze this data set to see what are the streams and the currents in the ocean. And there we can actually see our running time is actually much better than cubic. So in practice, it's like more like n to the 1.2. Don't ask me why, but so maybe this is the happy ending of the story. Thank you.
Thank you very much. Any question from the audience? Yeah.
Thanks a lot for the nice talk. I was just wondering if you can go back to the new free space that you were defining. Yeah, here. So it's with respect to a given curve, right? So yes. You consider everything based on a given curve, and you try to. So I was just trying to find a way to somehow relax the problem for a given curve, because there, do you agree that since you are talking about these canonical endpoints that you were expanding, so I was just wondering if that would make sense to fix somehow the potential positions of like matching points in terms of extremities for the subcurves of a given curve. In that case, you would somehow simplify a lot this setting with the discrete finite positions for your canonical point sets. I don't know if I'm clear, but...
So I'm not sure what you're aiming at. So the problem is actually more general than this, because I defined it like this, and then with approximation factors, we can actually reduce it to this. So we can solve the original problem within approximation bounds.
Perfectly, yeah, but what I'm saying is that...
You want to make it simpler by restricting the set of clusters, what directions they go, or?
No. Given that you are considering a specific curve and you do all this computation of free space for that specific curve, maybe it would make sense to somehow use some singularities on the curve, if any, for some situations in terms of canonical endpoints, and then
But I think that's also what we're doing in a way, right? So we are finding these canonical points, and then we're looking at...
do you fix them in advance?
Yes. No, we don't. The algorithm finds them. But how would you... I'm not sure how you would fix them in advance.
So maybe we should discuss offline, but this is very interesting. Thank you very much.
Thank you. Any more question? Okay, so let's thank the speaker again. Thank you.